Hey there! Accurate pollution control starts with airflow. Welcome to our explainer on measuring emissions using EPA Method 2. Here's our quick roadmap. We'll define Method 2, tour the Pitot tube, check assembly, and finish with calibration. Simply put, this method calculates stack gas velocity using gas density and average velocity head measurements. Let's dive into the overall view. This full manometer assembly is exactly what you'd use out in the field. At its heart is the Type S Pitot tube. For it to work, those face openings must be perfectly aligned. But reality is messy, right? You'll often run into field misalignments instead of perfectly constructed tubes. Surprisingly, slight misalignments are totally fine. They won't mess up your baseline coefficient if kept strictly under 10 degrees. Now, assembly precision is key. The temperature sensor must be carefully placed to prevent any aerodynamic interference. Also, the impact pressure opening literally has to be even with or above the nozzle entry plane. And you need a strict minimum separation of 3 full inches from the sample probe to avoid flow disruption. We'll tackle calibration next, but first, if you're enjoying this, definitely hit subscribe for more structured explainers like this. Watch out for duct blockage. If your probe assembly blocks more than 2% of the area, recalibration is mandatory. Calibration needs a specific wind tunnel setup, creating a stable, constant velocity of around 3,000 feet per minute. Here's the kicker. Perfectly aligned, isolated, Type S Pitot tubes automatically get a baseline coefficient of 0.84. Alternatively, standard Pitot tubes built strictly to EPA specs actually get a higher baseline coefficient of 0.99. So what actual data do you need to calculate the Method 2 average stock gas velocity? You'll need the average velocity head, absolute stack temperature, absolute pressure, and the wet gas molecular weight. You've got the tools and the math. Are you ready to take your first highly regulated stack measurement?